paper is Sim and Real Co-Training, a simple recipe for vision-based robotic manipulation, presented by Abhiram Maddukuri.
Hello, everyone. My name is Avi, and today I'm excited to present Sim and Real Co-Training, a simple recipe for vision-based robotic manipulation. Recent advances in robot foundation models have primarily been achieved by training on a large set of real-world trajectories. While these models have shown impressive capabilities, we're still far from being able to reliably deploy them in the wild, and it is unclear if continuing to scale up real-world data will get us there. Simulation is a promising tool to bridge this data gap, offering three key advantages: scalability through automated data generation, visual diversity through techniques like domain randomization and generative simulation, and task diversity, facilitated by large language models and procedural generation. Past work have made notable progress in leveraging simulation data through techniques like domain randomization and digital twins. However, these methods either require extensive manual tuning or are not as effective for more complex real-world tasks. Thus, in this work, we explore the alternative of co-training on a mixture of real-world and simulation data. Our study specifically spans two distinct domains: a panda robot in a real-world kitchen and a GR1 humanoid on a tabletop. From here, we look at three different types of data sets for co-training: real-world data, which has perfect alignment with our target task, but is expensive to collect; task-aware digital cousin data, which are simulated data sets designed to closely mirror real-world task semantics, but can have significant differences in terms of dynamics, individual object instances, and scene composition. These data sets offer scalable automated data generation, but face a sim-to-real gap and may require some tuning in simulation. And finally, our multitask prior simulation data, which we define as any task-agnostic pre-existing data set. These data sets offer high diversity, immense scale, and immediate out-of-the-box usability, but may have minimal alignment with the downstream real-world task. Putting everything together, our co-training pipeline first starts with the real-world task and some prior simulation data. From here, we collect a small amount of data in the real world, and in parallel, create and collect a small amount of data in our digital cousin environment, upscaling this data via DEX MimicGen. In the final stage of our co-training pipeline, we co-train on a mixture of real-world and simulation data, sampling our simulation data according to alpha, our co-training ratio. Diving into our experiments, we look at 11 different tasks with varying behaviors such as pick and place, door closing, and pouring. In testing different data compositions, we find that policies co-trained on a mixture of real-world, prior simulation, and digital cousin data outperform policies only trained on real-world data by approximately 38%. Remarkably, co-training with prior simulation and real-world data alone results in significant improvements in performance. Co-training with simulation additionally improves policy generalization to novel object entities as well as novel object poses. In investigating key elements for successful co-training, we look at the impact of different co-training ratios, which represents the probability of sampling simulation data in each training batch. We find that tuning this value has a significant impact on performance, with the best results coming from substantially sampling more simulation than real-world data. Aligning camera poses also matters. Co-training with misaligned cameras reduces performance by 18%. However, perfect alignment isn't necessary, as we can get good results with approximately aligned camera poses. Finally, even as we scale up real-world demonstrations in multitask settings, we find that policies co-trained with simulation data consistently outperform their real-only counterparts. This underscores that co-training remains beneficial even in data-rich settings. In summary, through our work, we have established a systematic study on co-training with the real world and simulation data, demonstrated the effectiveness of co-training with simulation data, and provided a simple set of recommendations to reap the benefits of sim and real co-training. In the future, we look to co-train highly multitask policies on longer horizon tasks and seek to investigate the underlying mechanism which allows co-training to be effective. For more information, please visit our website. Thank you.